Good morning, sir. My name is V. Satyajit from Tribly Department. Today, AAT topic is about an introduction to soft core processors and a biomedical applications. What are soft core processor? A flexible processing paradigm is reconfigurable hardware. Definition: soft core processor are processor code defined in hardware description language (HDL), like VHDL or Verilog, allowing deployment on FPGAs. Host platform implemented on field programmable gate array (FPGA), enabling plagiarism and tight hardware-software integration. Reconfigurability: they can be synthesized and reconfigurable post-deployment to match specific application needs and constraints. Soft integration: they support embedded software development operations with real-time operation systems and environment. Why soft core processors matters today? Agility, customization, and rapid development in embedded world. Acceleration in innovation, customization potential, lower NRC cost, ecosystem support, accelerated innovation, rapid prototyping enable faster deployment cycle, essential for evolving tech sectors like IoT and biomedical systems, customization potential, adaptability of instruction sets and memory hierarchy, meets domain specific, processing needs efficiency, lower NRE cost, avoid high non-requiring engineering cost of ASIC development, beneficial for research and low volume applications, ecosystem support, back can backed by mature development environment like Linux and Intel for seamless SDL to binary flow, soft core versus hardcore processors. A comparison: soft core versus hardcore processors. Implementation: soft core processors are synthesized on FPGAs, while hardcore processors are flexible in silicon. Flexibility: soft core can be customized and reconfigurable. Post deployment: hardcore offers no post fabrication flexibility. Performance: hardcore processor typically outperform in speed and power efficiency, but lack specification for custom tasks. Application stability: softcore excels in research, prototyping, and lower volume system. Hardcores are ideas for performance-sensitive apps. Architecture of softcore processors. Key structural components enabling flexible processing. Core pipeline typically flows a simplified RISC-style architecture with fetch, decode, execute, memory, and write-back stage. Memory system incorporate customizable instruction and data memory, caches, and memory mapped I/O interfaces. Bus interfaces includes configurable interconnects like Avalanche, Intel, or AXI Linux for free and memory. Custom instruction set allows inclusion of application-specific instruction for domain optimization, especially in processing. Popular software platforms. Popular software platforms. Key industries implementations: Noise to Microblaze. Noise to Intel 32-bit RISC soft processor for Intel FPGAs, scalable across Noise to profiles. Microblaze Linux 32-bit Harvard architecture processor with customizable cache, MMU, and instruction extension. Toolchain support fully integrated with Quarters and the includes IDEs, compilers, and simulation tools. Use case widely used in automotive, medical device, industrial automation, and academic prototyping. It was Design flow of software processors. Steps from HDL to deployment on FPGA. Hardware design defines processor and architecture using tools like Intel or Viva-DOS IP integrators. HDL generation, auto-generated HDL or customized in Rigol VHDL for synthesis on FPGA fabric. Software development. Develop firmware using IDEs with C or C++ support, includes device drivers and real-time software. Synthetic and programming. Synthesize HDL plays and produce the design and flash to FPGA for hardware installation. Deployment tools and FPGA integration. Toolchain ecosystem. Intel Quarters and Linux Viewer provides end-to-end design, simulation, and synthesis environment. IP integration. Drag and drop IP codes allows for quick system integration, including timers, URAs, ADC, and DMA engines. Simulation and debug include simulators in system logic analyzers and performance profilers. Software stack includes board support packages, RTO support, and firmware libraries for IO operations. Performance, power, and flexibility consideration. Clock speed limitation. Soft core operates at lower frequency, typically less than 200 MHz, than hardcore due to FPGA logic delays. Power efficiency. While not a power efficiency as a SIC softcore offers runtime adaptability and dynamic power control. Design flexibility. Reconfigurable logic enables domain-specific acceleration, optimized pipeline, and a custom instruction set. Area utilization. Resource usages can be tolerated by adjusting bus width, cache size, and footprint. Role of embedded system in biomedical devices. Empowering real-time medical intelligence with custom computing. Signal acquisition interfaces with biosensors, example ECG, EMG, to capture analog physiological signals for designation. Real-time processing, implementing filtering, feature extraction, and anomaly detecting using onboard logic or DSP unit. Portability and miniaturization. Support compact form factors, low power design ideas for wearable and implanted device. Data communication include wireless or wired interfaces, BLE units to transmit data to external system. Case study: ECG signal processing. Architecture of biomedical system, integration of sensors, processing, and communication. Sensors interfaces, analog front end with amplifier, ADC captures ECG or EMG signals for digital processing. Softcore processor implements processing, analyzes, and decision logic on FPGA fabric. Memory storage, on chip and external memory used for buffering signals and logic in events or waveform. Connectivity includes BLE or URADS modules for remote data access and system control. Real-time signal processing implementation, pipeline design, interrupt handling, custom accelerator latency optimization, implement multi-stage filters and QRS detectors using parallelized HDL module. Softcore process handles external sensors, interrupts, and time-critical tasks via real-time scheduler. Custom accelerator offloads compute insensitive tasks like FFT or valid transform to dedicated logic blocks. Combines direct memory access and low latency bus for signal response. Challenges: biomedical uses, validation and safety, power and heat, size and integration, signal variability. Performance benchmark softcore in biomedical task. QRS detection achieves 95% detection accuracy on MIT BHI dataset with latency less than 10 milliseconds on 100 megahertz noise, FFT computation, 512 points FFT completed in 1.5 milliseconds using hardware-assisted co-processing with microblaze power consumption. Complete ECG pipeline on FPGA consumes less than 250 milliwatt under continuous monitoring mode. Resource utilization. The soft-core DSP memory controller utilize less than 40% logic might range cyclones. Future trends in biomedical software processing, edge AI integration, energy harvesting, wearable system, telemedicine ecosystem, software security in medical devices, ensuring confidentially integration and availability in a embedded health system, data protection, firmware integration, access control, communication security. Comparison noise microblaze is a architecture toolchain ecosystem customizability licensing and cost. Open source software processors Vex Rix Pico RB32 portability application fit FPGA versus software in health tech. FPGA offers logic level customization parallelism and reconfigurable fabric ideas for signal processing. System on chip SoC combines hardcore CPU with network blocks for better integration and power efficiency. Softcore process soft IP embed in FPGAs and flexibility for rapid iteration and domain specific customization. Decision criteria choose depends on latency, cost, design lifecycle, and regularity overhead. Conclusion and keys takeaway. Software processors in biomedical innovation, flexibility and speed with software enables rapid prototyping, customization, and real-time signal processing. Biomedical integration, ECG, EMG, and wearable system benefits from software adaptability and low resource footprint R&D and beyond. Ideas for academic research, iterative development, and evolving clinical devices. Future headlines scalable to AI integration, telehealth connectivity, and next gen health tech demand. Thank you.